Hello, good afternoon, everyone. My name is Lenka Hamosova, and I'm a designer and visual artist researching AI-generated synthetic media at Film and TV School of Academy of Performing Arts in Prague. And now I will be moderating this next session. Please let me welcome researcher and artist Eyal Gruss, who will give a lecture on the recent developments in deep learning, especially in the context of synthetic media, computational creativity, design, language, and interactive systems, and how they can empower human expressivity, ideation, and decision. This can be a great insight for everyone who wants to experiment with today's AI creative tools and learn their potential and accessibility. Eyal is a new media artist and machine learning researcher who holds a PhD in physics. Eyal creates poetry, interactive installations, computer-generated art, algorithmic poetry, audiovisual performances, AI art, and online interventions. He has participated in many conferences and new media events worldwide, and today he's here with us. So welcome, Eyal. Thank you for coming. And I think Eyal disappeared. Oh.
It's been around.
Is it some kind of technical problem?
Let's wait. We should wait a bit.
Well, I think we lost Eyal.
I think he's been around just recently. I saw
maybe let's wait a minute or so.
Yeah, I see him here.
Yeah, hi, are you back? Can you hear us?
Yeah, so actually my machine crashed and I changed the computer. So okay. Hopefully it'll be okay now.
Yes, okay. So I already gave the introduction, so the floor is yours.
Okay, so thank you so much for having me. And thank you for giving me this considerably long slot where once I share my screen. Okay, well, I want to tell you about what I believe are the latest interesting innovations in deep learning for design and art and decision making. So I was introduced, I guess, properly, and I want to start talking about the deep neural networks. Ilya Sutskever, the chief scientist of OpenAI, said that if you have a large big data set and you train a very big neural network, success is guaranteed. I started being interested in neural networks maybe in 2001. I wrote this paper trying to model the armor of a Merkava tank to assess its performance against missiles. And at the time, I didn't know what I was doing, and I put together a few small neural networks to create what I learned years later is actually a deep neural network. And I want to talk about two types of networks today, and you can think about it as a machine. The first machine is an encoder. It can take an image or other media, and it learns features of this image and essentially does some mathematical transformations, and in the end, you get some kind of latent representation that we heard about before. And you can think about it as a dense semantic representation that the AI learns from the media. And we'll speak about the second machine. This is a decoder. And a decoder can take this kind of latent representation and decode it. And in the end, you would get back some kind of rich human consumable media as, for example, an image. And you can put them together, you get an encoder decoder. So you can put in an image, you can, the machine learns how to understand it, to essentially take out or understand the semantic content, and then you can render again an image. It can be a different image, or it can be a different kind of media. And once you have these encoder-decoder, generative neural networks, or maybe transformative neural networks, you can put in one of these kinds of inputs of rich media as an image, a video, audio, and so on. Do this kind of transformation. You get the latent representation. You may want to do some manipulations on it, and then you can translate back to a rich media. It can be, for example, take in a sentence in English, understand, translate to French, take in an image, understand what's in the image, write a caption on it, maybe take in some text and understand what's in the text, create an image out of it, and so on. We will see some examples in this talk. So what's interesting about these deep neural networks is that they learn the features, the essential parts of for example, from the image that are necessary to interpret the content, the semantic content of the image. And they learn these features automatically in a hierarchical way, where as you go deeper in the network, each layer learns higher and higher level of concepts. So here you can see the color patch is part of the image, and the corresponding gray patch is, you can think about it, is what this neuron sees that causes it to respond most strongly. And as we go deeper in the network, starting from the first layer that can recognize lines and colors, we get higher and higher level concepts. The second layer, you see these more complex patterns. And the third layer, you can see already these parts of objects, and you compose them hierarchically to get higher level concepts as objects. And in the last layer, these important features to understand what's in the image. For example, eyes is an important feature, or the text captions on the product. There was an interesting experiment done by Google after they purchased YouTube, where they trained a neural network to cluster different YouTube videos that are related to one another, maybe similar to one another. And they found a very interesting fact that neurons specialized in recognizing these high-level concepts like this face of a cat or face of a person. And what's interesting here is that these concepts were not, nobody taught the network about these concepts. These concepts emerged, or the network learned them as important concepts, probably very prevalent and important to understand the content of the video. So the network chose to actually have some neurons get expertise in identifying these concepts. And this may be similar to what happens in the brain. There's this famous experiment done with electrodes in human brains that show that people can respond very strongly to a very specific high-level concept, for example, Jennifer Aniston, and not to other similar concepts. So I want to start by talking about understanding images and what's in an image. So we can talk about recognizing what's in an image. There's this famous contest that was going on for 10 years, trying to recognize what's in an image. Is it a tiger? Is it a red fox? And so on. And this was a benchmark for the state of the art at the time. And you can see the improvement of the error going down from about 30% to 2% on the course of this decade. And so this is just recognizing the single object, a single essence in an image. We actually did an artistic project together with Eyal Gruss and a Batgirl using a different data set, not the ImageNet that I've shown before, but CIFAR10, with these very simple classes, and asking computer scientists to compete with the neural network of the time and see who recognizes more objects. And although these scientists work with these data sets their whole academic careers, the network, at the end of the day, beat the human participants. But we can say more than just recognize a single object in an image. We can talk about multiple objects with different locations and bounding boxes and repetitions. We can go even to further granularity to the pixel level. And for each pixel, you can determine to which object does it belong to. Or you can have multiple instances of the same class. I had a startup once, actually I'm wearing the shirt, a flat space, and we're not doing it anymore, so don't ask me about it, but we took floor plans and we did semantic segmentation to understand the architectural parts, and then we could build a 3D model that you can walk in this floor plan, but just based on the bitmap image with no CAD. What's in an image? You can ask maybe textual questions about an image. Maybe you want to count the bananas. Maybe you want to ask something about the color of a shirt that is obfuscated. You can ask questions, and maybe you also want some explanation. So what is the color of this bus on the top left? It's blue. Why? Because the model is looking at these pixels. How many flags, pink flags, are there? There are 2. And what is the model looking at? It is actually looking at these flags. So probably it's counting the right thing. These explanations can be very important to debug the model and to build trust in the model. We talked about bias today. And in this very interesting work, they used a model that can discern if the person is a doctor or a nurse. But the thing is that the data was biased. Most of the doctors were men and most of the nurses were women. And if you naively train the model on this data, then on the top row, we have here a nurse, and the model predicted she's a nurse. This is correct, but why? So you see the attention here, the model is looking at her hair. Maybe that's not relevant for her being a nurse. And on the bottom rows, the woman is a doctor, but the model again thought she was a nurse. Why? The model is looking at her hair, which is not relevant. So they created a gender equal data set. And once they trained it on this equalized data set, now the model recognizes that this woman is indeed a doctor. The model is not looking at her hair, looking at the stethoscope. And also here, now it still knows she is a nurse, but looking only at the uniform and not at the hair anymore. So we don't only want to recognize what's in an image, we want to do the recognition for the right reasons. And this kind of interpretability is very important. If you studied physics or math, you may remember that the tutor wanted to see not only the solution, but also the way to the solution to make sure you didn't just guess. You weren't only lucky. So in this case, we are trying to understand the relation between objects and the image. So this is more and more elaborate tasks of understanding the visual domain. And here the model doesn't only output the correct answer and the heat map, but also gives us a short algorithm for the human, a short list of operations, if you want, the way to the solution. And we can use this to make sure that indeed it got to the correct solution for the right reasons. So what's in an image? It's not only the objects and their location, it's also the relationship between the objects, and not only the geometric relationship. Maybe it's a functional relationship. And maybe the relationship between objects can have some significance to understanding the image. For example, here considering trying to understand what is going on from a social point of view. So a person is pointing at something and another person is looking at someone else. And what is happening here? Did he tell a joke? Does he want the pancakes? So you can see that the question of what's in an image, it's a very complex question, and it may not be solved yet. And there's this famous image that is usually used in this context. So we see here Barack Obama, who's the US president, and one of his staff is standing on a weight, and Obama is pressing it with his leg, making him seem heavier, and all the people are laughing. So what kind of human social knowledge do we need to try to understand what is happening here? It's not enough to recognize that this is Barack Obama. You need to understand something about humor and how people consider their weight and the physics of pressing the weight with the leg and so on. So I hope you can see that there is still a way to go if you want to be able to interpret even a single image. And once we do have models that are very good at understanding blueprints, understanding images, we can go back to this idea by Goodfellow, the father, the inventor of the generative adversarial network. And here he's talking about having a universal machine learning or a universal engineering machine to do model-based optimizations. So if I can take a blueprint of a car or a visual image of a car and understand the relationship between that and its aerodynamic behavior, for example, then I could use this model in order to create a more aerodynamic car. And we're starting to see this idea in several places, sometimes in product design, maybe in a molecular or a drug design, but there is still yet a way to go to actually use the capability of a model to understand an image in order to optimize its qualities that may not be just aesthetic. And you can think about my story from the beginning about the armor of the Merkava tank. And once you have this model, maybe you can design better armor. So, but we're not here to talk about only analytics. We're here to talk about generative models. And Feynman said, what I cannot create, I do not understand. So it goes both ways. Probably you heard already about generative adversarial networks, and you know these people because they are in every presentation on the subject. These faces are already some years old and are, of course, computer generated. And you can get as many as you want, and even today we do have better quality. And this uses a generative adversarial network. The generative adversarial network is, but let me jump a few years further. We have a generator. This is the network that draws, that paints these images, which are fake or computer generated. We also have the real data. So these real actors like Johnny Depp and Gal Gadot. Now we also have a second network, a discriminator. I like to call it a curator. The discriminator's job is to discern if the output of the generator is fake or is it real. And they have a conversation between them. The generator tries to deceive the discriminator. The discriminator tells the generator if it was successful in deceiving it or not. And in this iterative cycle of training, in the end, we can throw away the discriminator. And it turns out that this method gives the state-of-the-art results in many generative tasks. Now, this was not conditional. We just generated celebrities. But we can talk about conditional GANs, and this was already mentioned, the pix-to-pix image translation by Isola, where you can take in as an input some kind of image in some kind of domain, like black and white image, and do this generative task to turn it into a color image, or you can turn a map into or into night. I think someone is having his mic open.
Please, could you turn off your mic? Yes, thank you.
And you can see in this interesting example, now the input is only the contour. And in the middle columns, you can see the ground truth. And the output of the model taking the contour and outputting an output that looks photorealistic and is diverse and is original and maybe can be used to get new ideas. But the small problem here is that we needed these kinds of pairs in order to create this transformation. So the next iteration was doing it unsupervised. One of the algorithms is called cycle gun, where you can do this kind of translation, for example, horses to zebras or vice versa, without these pairs. So now we don't have to put the camera to capture an image in the day or in the night. So we can do transformations like summer to winter, or transformation between various artists where we don't have corresponding images. Also for these horses or zebras, we don't have the corresponding images between them. We just have a set of horses and a set of zebras. And using this kind of cycle consistency, so making sure that a blonde translated into a brunette, translated with the reverse transformation back into a blonde, you get something close to the original blonde. And then you can put this into a gun to discern between the real blonde to the fake blonde created from the original brunette. And putting together the cycle consistency with the gun principles, you can get this kind of unsupervised image-to-image translation. I use this in my work with Anadas to create these vegetable faces in the style of Archimboldo or Hanoch Piven. And this work is called the electronic curator. And it talks about this fact that in our GANs, in our current day generative algorithms, we have not only an AI painter, but also an AI curator. And people like to say that in generative art, the role of the human maybe is only to do the curation. And what we're saying here is actually in today's modern algorithms, the machine is also doing some form of a curation. So in this work, we create these live vegetable faces, and then a curator decides if it's worthy enough, if it's a good enough portrait to put in the museum, and write some curator text about it. And we didn't have Hanoch Piven draw these for us. We just did Google vegetable faces and Google portraits, and with a very small data set, you can learn this kind of transformation. And this has already worked some years ago. I want to talk about storytelling. So what can we do with all this technology? Well, generative algorithms get better and better. This is a big gun. It can generate the classes, 1,000 classes for ImageNet that I mentioned in the beginning. With these outputs, all these images are computer generated and they look photorealistic. Okay, but as an artist, I'm not sure I have much to do with it. And there was this interesting Twitter thread by famous new media artist Mario Klingman, where he used this kind of big gun and he got these images that are maybe half nonsensical, but he put them in some order and he imagined a story and he told some kind of a story that he invented, that he was walking in the desert. He invented this after the fact. And he found this bug and he took it to read this text that was written in some alien script. And then he went to the spaceship and so on and so on. And I found this more interesting than the photorealistic images. And I wanted to use this kind of big gun to tell my story. I had a problem. Big gun is only a decoder. So it can only take the latent representation or some random latent representation and generate an image. And maybe you can control the class, but you cannot control the specific content. So you remember, it's only the decoder. I don't have the encoder. It's blind. So what I did in this work, WonderGun, I used evolutionary research to solve this problem of inverse rendering. So these are the images that I wanted to recreate with this big gun. And it's probably choppy because of the zoom, but I'm showing here like the best result in the process of using evolutionary research to try again and again to find the latent representation that can recreate this original target that, again, the model is blind, it cannot see. And in this case, this is in a second you will see an image, a photograph I took of my dog. And using this kind of process, you can see that the recreation with the big gun is not exact, but it's quite good, and it captures the semantic of the image. And I wanted to show you the last one, which I think is maybe the most interesting. And here, something is recreated. It doesn't look really human, and actually ImageNet does not have a human class in it, only sporadic humans. And you can see that the recreation here of this photograph of a friend of mine, Savion, who is an actress and a dancer, and she's wearing these puffy wings. The recreation is far from exact, but it captures something of the semantics. And I think this is more interesting than capturing the exact style. So I went on to create this experience, interactive experience, WonderGun, where you start from a memory. This is Rana Das walking in the forest, and you can see this is a visual journey that is based on the attempts of this blind painter to try to paint something more and more similar to this a target image that it never saw. It just got cues if it was close or not, and it tries again and again. And with his evolutionary research, doing different mutations and recombination, until it gets more and more similar to my original memory that I tried to recreate. And I think this creates an interesting visual journey. I think about it as like maybe floating in a dream. And actually it's interactive. You could press one of these quadrants, and then instead of this original image, it will try to zoom in and recreate this specific quadrant. So I think about it as like maybe navigating within a dream where you start from some memory, but then you see something more interesting and you go there, and so on. So this was telling a story with images, and we can also tell a story using text. And you probably heard about GPT-3. It's, I think, the most advanced generative text model where you give it a cue or a seed, an initial text, and it can continue it. So actually here I'm showing GPT-2, the former version, and I wrote a short text about this talk. And so in bold, you can see the continuation. So, and the continuation was actually, I said I will also exhibit my digital artwork and perform live demos. So this is not for today, but, and it continued of the new generation of deep learning algorithms. I will also present my latest work, The Art of Deep Learning, which is a collection of short videos and slides that demonstrate the power of deep learning. There is no such talk, but I like this title. And then came out a GPT-3, and this is not widely available, but there are some hacks how to interact with it. And I was in a game that allows you to interact in some way with the GPT-3, the current version. And I don't remember the prompt, but this is what it had to say to me. And I think it's very imaginative, and it's amazing response. Let me read it out to you. So this is all the computer. I'm a dragon, I'm a dragon, I'm a dragon, you say to yourself. You're not a dragon, you're a freak, a voice says. You look around and see a large head with two red eyes. It's the head of a dragon. Who are you, you ask. I'm you, but more badass, he replies. That's stupid, I'm dreaming. Well, wake up then. So this is amazing. And I think we can also think what it means. It learned this reading many texts from books or from the internet. And this moves me, but maybe we can learn something from this about what moves people. Maybe it's not so difficult. Maybe you just need to use the right kind of a witty genre to get this emotional response. And a very different end, programming is a very strict task. And they were able to just give a prompt to GPT-3, say, I want a JavaScript with two buttons, one to accumulate the price and one to make it lower by $5. And you get code. And it's very, if you have one byte wrong in the code, it won't run. And sometimes it doesn't work, but there are enough times that you get this correct code that you can actually run. And personally, I'm very bad at JavaScript, so I hope in the near future I can use this to do my JavaScript for me. And we will be seeing here, already seeing this common theme of we want to give the direction to the machine. We want to give the ideas to the machine. I want the machine to do the heavy lifting, do the task for us. So we talked about images and about text, and let's combine them together. So in 2016 came out DesAIgn, and it was very innovative at the time. It was able to take this text, the bird is yellow with gray wings and so on, and generate this photorealistic image of a bird. It works for birds and for flowers. And at the time, it was groundbreaking in the sense that people thought it would take maybe one more year to get to this achievement. And they were surprised. And I will mention this kind of a theme again of researchers being surprised of the acceleration of the domain. And this tells us something about how fast we are moving forward. So this was the state of the art just a few years ago. And every year we got some improvements. So this is the same one, the DesAIgn, the bottom row are the generated birds and the flowers. Again, conditional generation based on this exact text. And then we had Attention Gun, who can also do maybe lasagna, not very much better. But maybe you heard about cherry picking. If you have Tinder, you probably put your best images there. And also machine learning researchers put the best results sometimes in papers. So you do need to test yourself if you want to get a real world evaluation. So I put in some sentences here, and the images were fine, maybe not good enough for the creative industry, but of course good enough for poetry. So together with Vert Charuti and Eretz Sapirstein, we created in a 30-hour hackathon this project.
Draw a deer, a female deer. Re, a drop-on golden sun.
ایمان بیاوریم به ویرانه‌های باغ تخیل.
ואז גם אני יכול לנוע מהר מהאור.
물끄러미 바라보다 고운 난초를 건네노니.
به ابرها که فکرهای طویلم بودند.
성낸 까마귀들이 너의 새하얀 빛을 시샘할까 두렵구나.
ברקת.
So this was using several machine learning models, namely speech to text, and then translation to English, because Attention Gun works in English, and then Attention Gun. And this was a state of the art just maybe up to 1 year ago to transform text into image. And maybe you didn't understand the Hebrew or this lovely Persian or Korean, but maybe you could get something of this image, something of the atmosphere, maybe some synesthetic experience, maybe some more universal experience. And this is some kind of a visual poetry based on the text. And then came DALL-E, and this is from a few months ago. And when I saw this, and I'm talking about these things for some years now, I said, wow, I didn't believe that a machine can do this. And what DALL-E does, it can take a text description, for example, a snail made of harp, or a snail with a texture of a harp. And it can generate these images of, well, you see, combining the concepts of harps with snails, either to create a harp-like snail or a snail-like harp. And, this text probably, it's not on the internet. This visual concept, combining these two objects, probably was never thought of before, never rendered before. And this model is able to take this text and not only understand it, but invent a new idea, combining these two objects to something new. Someone asked before in the chat, but can AI innovate? Can it create? And I think this is one of the most interesting examples, most recent ones also, of this happening. So we have here the ability to take a text that was never seen before and of a concept never thought of before and create a visual rendering of it. And this is amazing. Unfortunately, they didn't release the full model. And in a follow-up work, hey, remember in the beginning, I talked about the neuron specializing in this very high-level concept and Jennifer Aniston neuron. So in this example, they speak about Halle Berry, but what they show is that maybe humans can respond to Halle Berry either as an actress in costume or a sketch of her or her name. So this would be the response of, I'm not sure exactly it's with electrodes in the brain, of course. And they show that the Clip Neuron can maybe do something similar. So not only understand this high-level concept, but also do it in a multimodal way. So this is Spider-Man, and this is a sketch of Spider-Man. This is just the word spiders and the spider web. And fortunately, it's Spider-Man and not Batman, although there is a small bat here as well. So, and this is, again, based on the DALI and the Clip framework that was only partially released to the public. And so some people, and it's really a really interesting time because we find ourselves, I think of myself as like an independent researcher or an indie artist, and we can take these partially released models and try to push the boundaries of the state of the art. And several people were working on it, the same day that the code was released, and I was one of them, and I created this interface you can access called WonderClip, where you can start from this textual description, and it tries to render this image. Now, it's not photorealistic, but for the first time, I could render something that I could never do before. In this case, rainbow unicorns. I could never render even a regular unicorn, and it's not perfect, but we're on the way. And you can think about the future, being maybe able to generate photorealistic things, maybe animations and videos, and we don't have access to the full model, but people were able already to apply what was released to create this kind of new concepts. For example, this one by Gene Cogan, a banana performing stand-up comedy. So I'm not sure if you can find this kind of images and in the internet. Maybe this is a new concept, and that the algorithm, the model was able to render just based on this text. And if I mention animation, Gene Cogan was also one of the first to release this kind of animation where he was able to apply this model iteratively based on the text and based on the previous image to create this kind of short animation. And until recently, I didn't have the courage to imagine what will be coming. And now, for the first time, I'm very much optimistic about our ability in the near future to be able to generate not only text and not only image and not only conditional ones, but also animation and also videos. And it will be a very interesting near future. The art of robot war. So we talked about the generative algorithms, and we talked about discriminative algorithms trying to understand what's in an image or generate an image or translate between two different medias. And there's also another kind of algorithms where you have some kind of an agent or a robot trying to solve a task. And this is sometimes called, or some of these methods are based on reinforcement learning, where an agent, a virtual agent, interacts with an environment, and you give it cues. For example, like a punishment or reward. If it does something good, the score goes up. If it does something bad, the score goes down, and it tries to learn the optimal strategies of behavior. And in this example, and this slide is already some years ago, from 2014, I think, but you can see that all these old Atari games were, the computer learned to play them with the same algorithm. And you can see the comparison of the computer player to the human performance. And this is like the average human, this is the professional human. And you can see that there are many games that the computer can play better. And again, this was one of the first works, and it got better since. And it's very interesting to consider some of the strategies that these algorithms can learn. So for example, in this famous breakout game, you see the computer is quite good at this point of training. But now they will show us what happens if you do even more training. And what turns out that the model was able to learn this optimal strategy, this tunneling strategy, creating this small tunnel, putting the ball inside, and then you get all these points and you don't have to fear capturing the ball so much. And this kind of strategy could be learned just from doing self-play. And then we had Alphago. So you may have remember, I already mentioned twice, people being surprised by the rate of acceleration. And maybe here is the example where this was most significant. Go is a very complex game. It's much more complex from a mathematical algorithmic point of view than chess. Number of possible states, more than atoms in the universe or something like that. And this was one of the biggest challenge for computer scientists. And it's 2015. If you would ask an expert, they would say maybe it would take 10 years, a decade, to solve this kind of challenge. And if you were following the news, year by year, they got better. They first beat the European champion, and then the world champion, and then they played online and got a perfect score without revealing their identity, and so on and so on. And this was based on both on self-play in reinforcement learning, and both on reviewing all the history of hundreds of years of human innovations in Go. And then what they did in Alphago 0, they said, okay, let's forget about all this human knowledge. Let's just use self-play. And this algorithm was later able to beat the original Alphago, and of course, many other humans. And then they showed that it can also be applicable to other games, and so on. So this is a very significant challenge that was solved. But this is a board game, right? So if we go, for example, to this modern computer game like Dota, we have here this live action involving teams of 5 players. And we have much more a longer time horizon than chess. And there is fog of war. You don't see all the board, just part of it. You don't have the full information. You have a much more complex action space. So the number of possible moves you can do in each turn is much larger. And there are much more details to pay attention to. And you want to play it in real time. It's not turn-based. And again, if you follow the advancement like year by year or month by month here, the OpenAI in this case was able to beat a team of human champions already in 2019. And let's see this.
To prevent seekers from using the ramps, The hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learned.
Do you hear the audio?
However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter.
So they had a simulation where you play hide and seek, the blue one wants to hide.
In the last stage of emergent strategy that we observed, the hiders learned to lock as many boxes as they can before constructing their fort.
Strategy where that
strategy that we observed,
they didn't think that this was possible, but they learned the strategy that they can go on the box and jerk it around until they get to the above the barrier.
In the last stage of emergent strategy that we observed,
so this was a very
neural network directly outputs steering angles to the net.
And let's go from computer game to the real world. So we heard today some things about autonomous vehicles. And here, I'm not sure that if everybody knows about this. I was surprised to find out that this vehicle was used in the 80s and 90s in the nav lab in the United States, using a neural network to control this vehicle. Wait, I skipped it.
Neural network directly outputs steering angles to the nav lab steering wheel.
I guess this is
suddenly an unexpected obstacle appears in front of the van.
But I was quite surprised to learn that this technology was already tested in the 90s. And if we jump to 2016, we can see here the Tesla Autopilot V2. They say in the beginning the driver has to sit behind the wheel for legal reasons. There are various levels of autonomous vehicles requiring different regulatory requirements. But essentially you can see he's not touching the steering wheel. He will sit like this all the ride. Actually, he will get out later and the car will park itself. And 1 year later, you could see in the end of 2017, you can see Google Waymo. And here the passengers actually sit in the back. So they will not be able to intervene if they need to. The car, in this case, would have to stop by itself. But you know, this is in Phoenix, Arizona, in suburbs. I don't think this will work, say, in Jerusalem. I'm very frightened to drive in Jerusalem. But last year, Mobileye released this amazing video from their car riding in Jerusalem. And this is titled the Unprotected Left Turn. And you see the car here trying to take a left turn, and it actually has to aggressively go in the traffic. And maybe this is not formally legal, but you have to drive like this in Israel if you want to get to your destination. And at least by their claims, this is fully automatic, and the car at some point just carefully goes a little bit, budges forward until someone stops, and then it's able to complete this unprotected left turn. So this was very surprising for me to see. So there are various levels of autonomous vehicles, and the first one is referred to sometimes as hands-off or eyes-off. This is level 2, level 3. And on the right, this is the Waymo, where people sit in the back and they can maybe take a nap, so maybe mind off. And I like to speak about this as the dashboard metaphor when I try to think or consider how these kinds of generative algorithms, how these kinds of agents can help us doing our creative task, or design task, or diagnostic task, and so on. And while the future may be going to the fully automatic solution, I like to think about many of the technologies we have today as tools that we can form with them some kind of a hybrid designer, a hybrid artist, a hybrid doctor, that combining our human capability with the model's learned capabilities, we can, in this form of a dialogue, having this rich dashboard and getting the model showing us why it took decisions and giving us insights to help us build trust in the model and to help us in our decision making. I think that this is the way that I see these tools today, at least how they help me express myself as an artist. Self-promotion, we do have, as part of this, following this conference, a hands-on tutorial that is given Tuesday, and I think maybe some of the attendants here are registered. Eyal told me there will be details in the website tomorrow for whoever didn't register yet. And in this workshop, I will talk about the subject that I didn't have time to talk about today, video-to-video translation and deep fakes and avatars, and how we can take an input video and use it to puppeteer, to control a different image. Actually, this is based only on a single image, so I'm here controlling an avatar of Ilana Glazer, and what we are seeing here is a web interface that I built over Google Colab, allowing anyone to run this kind of live avatars using your own materials and just the web browser and the good internet connection. So I would be happy to have you in this follow-up tutorial on Thursday. And in this context, the last thing I want to mention is that Nvidia released Maxine some months ago, and this is a very technical use case for this generative avatar deepfakes, where to save bandwidth, like we have the issue with Zoom now, they transmit, say, a low resolution image, and then they use generative methods on the other side. And in the limit, you can take it to doing like avatar generation on the other side in order to just to save bandwidth. But I think this goes back to the theme already mentioned here, that we may be approaching a place where we do not need to generate the media ourselves, or we do not need to distribute the media itself, but we can actually be the director or be the script writer and give the model just our idea or the instructions. Or here, you could broadcast not the full media, but just the skeleton or just the description, and get generated media, a synthetic media on the other side. So maybe we are moving from an economy of distributing media or having to manually generate media to a world where we will be, as David Avidan, Israeli poet, said, the machines will create the text of the future. He was a poet, but and then he continued, and we shall be the guiding mind and the confirming eye. And I think that for me, looking into poetry, looking into visual image creation and manipulation, and looking forward to doing the same for video, only in recent months, I start believing that this prophecy is coming true now. So this is what I had to tell you about the latest or historically significant and the latest innovations in deep learning and generative modeling and computational creativity. I think we have actually 15 minutes for questions or for discussion.
Yes, thank you, Eyal, for a really low lecture with many mentions of different AI models, and also like thank you for choosing this nice narrative of how to present them, because I know there are so many of them, and it's sometimes a huge overload of information when talking about it to people, like which one to choose, and I think you're choosing well. So now I would like to encourage the audience, if you have questions, please write them in the Q&A. It's on the bottom of the Zoom interface. And until some questions pop up, maybe I would like to ask a question regarding your last idea that we will maybe switch from distribution of media to distribution of ideas. And I think it's touching the fear of a general audience of manipulation, and like that when we will be confronted with synthetic media, so it's not my real face, it's just the skeleton and the rest is rendered. How can we be sure of the origin of the visual or audiovisual information? And this is a huge discussion at the moment. And so what is your take on that?
So people are working on also detection methods, and people are discussing the regulatory possibilities. Maybe you need some kind of a watermark like you have today already in printers. It's to make sure people do not counterfeit money. But I think that it opens up an interesting discussion about actually what is considered real and what's considered fake. Because, when you prepare, say, a promotional video, you do use different kinds of image manipulation. Maybe you have a pimple you want to hide. I'm actually using the improve a light filter of Zoom. Maybe you want to fix something in the colors. So you need to understand, when does your manipulation change from a stylistic manipulation to a semantic manipulation? On the other hand, maybe you are impersonating someone else, but in this spectrum, I think the non-trivial thing is to understand, well, finding manipulation, you would find it many times, but I think what's maybe not well defined is what manipulation you would consider to be a semantic or a substantial manipulation that you would want to make people aware of or forbid. And I think this is a non-trivial solution. But there are algorithms to find, this specific algorithm for doing deepfakes and the specific counter algorithm to detect it. This is research going on all the time.
Yeah, and that's probably going to end up in this cat and mouse game, at least as it happened in the past. Yeah, I completely agree that we need to have an agreement about what is actually real and whether what we need to still keep as reality. And also maybe regarding this lecture could also lead as some kind of introduction for or maybe a call to action for people who would like to maybe start experimenting with synthetic media. Also maybe students who would like to try and implement these new tools in their practice. What would be your advice for them, where to start, or how much are these tools accessible for anyone who's interested?
Personally, I found myself interested more and more in the last years in making this technology accessible both to the general public, but specifically to artists, and using this kind of Google Cloud computing resources. I, like many other people, try to take the recent code that is out there, and it takes time until it gets into your phone app, or to some specialized software, and we can just wrap it in some code and allow you with a few clicks of a mouse to run it in your browser without installing anything, without any special equipment other than Google's cloud computation. And actually, I put it in chat later. I curated this list of many of these collabs or notebook environments that with maybe very little explanation, if you will come to the tutorial on Tuesday, I will show how to use some of them. You could use them to do generation and manipulation with the latest algorithm and using your own media, your own text, your own image, your own video. I will put a link in the chat later. And we are seeing more and more environments like Runway ML and plugins for Premiere or Photoshop that allow easier access to these technologies. And specifically in the context of synthetic media, I also think that making this accessible is important from a social point of view to help people not only learn about responsible usage of this technology, but more to be aware of the various possibilities of synthetic media and be more skeptic when they consume various media.
Yeah, I totally agree. I think it's really important to be able to step in that process now, especially as designers, because we see that these synthetic media are being already implemented in different apps like Photoshop neural filters, and that allows you only to interact with it as an end user, but you cannot step in and explore how it could be used in a different way. So in that way, it's already a closed use of this, something that's otherwise really large potential.
So the collab, it's for limited usage, it's free. And this is based on open source code, and you can actually, with a button click, go in, and if you don't have to, but if you want to, you can go in and change the code. So you have complete control. And then, so I put a link in the chat, and you can feel free to follow up if someone is interested in some of these techniques. A lot of the things I showed in the talk today, there are corresponding either web interfaces or collabs to allow people to play with these kinds of algorithms.
Yeah, I'm actually not sure whether our audience can see the chat. Yes, okay, probably is. Cool. Okay, so are there any questions from the audience or from the other speakers and panelists? Yes, Mr. Marks. You need to turn on your mic, please.
Sorry, I am watching the whole thing and prepared the whole program. I'm just wondering about your reaction to the following question. When I saw a couple of presentations, especially the stuff on architecture by Stanislas, you can see the need for really good understanding of a specific sector or specific problem you want to deal with as a designer or artist. So I wonder whether all these pre-programmed manipulation tools, what is your feeling about their use and their long-term use and sustainability vis-a-vis the creative class? Because as we've seen with the architecture and several other examples, in order to be really in charge of creative process, you seem to be, you seem to have to master very specific small segment so that you really have some power over the manipulation and experimentation with the AI. So what would be the difference between all these general kind of simple as if toys and using the AI in rather serious experimental way we've seen several times during the day. So these are two different things, but I want to see your reflection as somebody who understands also the algorithms of math behind it. Thank you.
So let me know if this goes to your question, but what I'm thinking about is the importance of human knowledge and how to combine a domain-specific prior knowledge into the decisions or the outcomes of the algorithm. And when I was working on the taking the picture of the blueprint of the floor plan and making a 3D model out of it, it was working nice. Actually, we had like the first online demo doing it in almost real time. But you know, sometimes we got a toilet, and inside the toilet there was another smaller toilet. Now, there is never in real life, at least in the architectural life, there is never a small toilet inside a big toilet. And it's very basic common sense, but we had to manually put in rules that, well, this was the easiest way to address this, to tell the model that one object cannot be inside another. And if you think this is the case, forget about the smaller one, take the bigger one. And there is a lot of work going on how to put in this prior knowledge, this domain-specific knowledge, this common sense into the model and prevent the model from doing stupid mistakes. So I think, and there's a lot of place to still to advance in this challenge. And of course, when you get to the medical domain, when you get to autonomous systems like driving on the road, you do want to put in this checks and balances. And this also goes to the interpretability and explainability of the system, that so you can make sure it is making the right decisions, that you can build trust in its decision, not only taking the final number, the probability it gives you, but to see that it gets to this result from I forgot the word, severe, in a sensible way. I'm not sure if this addresses your question.
Not really. It doesn't matter.
Ernest, I think that we should continue with the next panel. So thanks so much, Eyal and Lenka, for moderating this session.
Thank you.